A flashlight beam can bend even if nothing around it moves. It bends because space itself is curved, geometry, not motion. The immediate takeaway is simple. Curved space changes what counts as straight, so paths curve. Think about a marble rolling on a shaped bowl without any shove. The bowl can sit still, yet its shape redirects the marble. Gravity works that way, but it sculpts spacetime, not just surfaces. In that geometry, the straightest possible routes are called geodesics. Those routes look bent to us when the background space is curved. Nothing needs to stir for geometry to steer every path. Quick mental image: draw a grid near a massive sphere, then stretch it. The lines dip inward while the sphere can remain completely still. Light follows the warped grid, so its beam grazes and deflects. Planets do the same, tracing curves that feel like natural straight lines. You are not watching a hidden force tug invisible strings. You are watching rules for distance and time change with position. That rulebook is the metric, which sets lengths and durations everywhere. Change the metric's shape, and geodesics tilt without any push. Eddington's 1919 eclipse photo showed starlight bent near the sun. Astronomers saw geometry at work, not a gust of celestial wind. One-sentence recap: bends appear when straightness itself is rewritten by curvature. You step outside at night, and starlight grazes the sun's edge. Spacetime curvature means geometry is not perfectly flat around mass. That matters because geometry dictates every free path, including light rays. A geodesic is the straightest path allowed by the local metric. The metric is the map that assigns distances, angles, and clock rates. It quietly tells matter and light how to move without pushes. When mass or energy is present, the metric's shape is altered. That change shifts nearby geodesics, so previously straight paths now veer. Mechanically, Christoffel symbols encode how coordinates tilt within that map. Those symbols steer motion, even if the mass sits frozen. You could hold the source fixed and still trace curved tracks. Example: in real terms, sunlight deflects 1.75 arcseconds at the sun's limb. That tiny angle equals a coin's width, seen kilometers down a road. Eddington measured it during a solar eclipse, comparing star positions carefully. The match favored curved geometry and dethroned Newton's simple deflection. Lensing today repeats this test with galaxies and radio waves. One-sentence recap: the metric's shape alone bends paths, even with still sources. Picture a silent star field with a heavy sphere hanging motionless. A static spacetime is one whose metric stays unchanged through time. You care because predictions become cleaner, while real bending still appears. The field is present even when the source naps on camera. Outside a quiet spherical mass, Schwarzschild geometry rules every trajectory. Its metric is time-independent, though its spatial curvature is real. Riemann curvature stays non-zero, so free paths still arc around mass. Nothing must wiggle or rumble for orbits to shift slightly. Mercury's orbit shows this, with perihelion drifting over the years. The observed extra precession is about 43 arcseconds per century. That number solved an old puzzle without a moving sun explanation. Planetary paths are geodesics in a curved, yet static stage. Their ellipses rotate slowly because the background geometry is not Euclidean. You can simulate this with marbles circling a well-shaped sheet. The sheet holds still, yet the tracks slowly twist with each lap. Astronomers confirmed the effect by comparing century-scale observations and theory. In the records, the secular drift matches curved geometry's prediction. Net result: static curvature redirects motion, while the source can stay still. Two astronauts float shoulder to shoulder, helmets reflecting a distant Earth. Geodesic deviation describes how nearby free paths change their separation. You care because tides, squeezes, and stretches arise without physical contact. The equation links spacetime curvature to how neighboring paths converge or spread. Where curvature focuses, lines meet. Where it relaxes, lines drift apart. No thrusters fire, yet gaps change, set by geometry's second derivatives. Tiny test: drop two balls a meter apart and let them fall. Near Earth's surface, differential acceleration is only a few micro-g, that equals roughly 3 micrometers per second squared, of changing separation rate. After 1 second, the gap differs by about 1.5 micrometers. You never touched them, but the geometry quietly edited their distance. LIGO hears the dynamic cousin when waves pass and squeeze space. Static fields do similar things, though the pattern stays unchanging. Many satellites feel this as their relative orbits breathe over time. Engineers model the deviation to keep formations tight and safe. Example in practice, Grace mapped Earth's gravity by tracking distance changes. The measured wiggles matched predictions from geodesic deviation precisely. What to remember, curvature choreographs relationships, while objects can look motionless. Far from any visible matter, galaxies still recede from one another. Vacuum curvature means geometry can curve, even when space seems empty. You care because cosmic acceleration likely reflects uniform vacuum energy. The field equations allow curvature from a constant, the cosmological constant. That constant behaves like negative pressure, spread evenly through space. It changes expansion rates, even if galaxies only coast with inertia. Space does not flow like wind, the map scale factor grows. Distances between unbound galaxies stretch, so redshift accumulates over time. You can mark a megaparsec, then watch recession near 70 kilometers per second. That number is h0, a snapshot of today's global expansion. De Sitter space is the ideal curved vacuum with a fixed scale. Its horizon sits near c/h, about 14 billion light-years. Photons crossing that geometry redshift relentlessly, while sources need not move. Supernova surveys trace the acceleration by comparing brightness and distance. Baryon oscillations and lensing cross-check the same cosmic profile. One-sentence recap: vacuum energy curves geometry, so expansion proceeds without motors. Imagine a quasar's light skimming a massive galaxy, then splitting into twins. Gravitational lensing is light following geodesics through curved spacetime, like glass. You care because lensing weighs dark matter and maps hidden structure. The curvature near a cluster deflects entire bundles of rays into arcs. Multiple deflections can arrange rings, crosses, or stretched mirror images. Time also stretches there, so paths arrive with measured delays. Mechanically, the potential well tilts the metric, steering null geodesics inward. Angles accumulate along the journey, producing apparent images around the lens. Rule of thumb: strong lenses bend light by arcseconds to tens. One famous example drew a near-perfect ring about 2 arcseconds wide. Another cluster produced dozens of images across many arcseconds of sky. Quasar pairs can flicker with days-long offsets between lensed images. Shapiro delay adds microseconds for radio waves grazing our sun. Astronomers solve these mazes, then reconstruct the lens mass precisely. So the picture is, geometry alone redirects photons, while sources stay serene. Stand by a mountain ridge at dawn and lay down laser triangles. Curved space means triangle angles need not add 180. You care because gravity becomes measurement rules, not a pulling force. The metric is the rulebook assigning distances and durations to intervals. Clocks lower down tick slower, while nearby rulers also change subtly. Stationary observers still disagree, because geometry assigns different ticks in yards. No mysterious ether is required and no medium must flow. Relationships among instruments define shape, not any hidden substance. GPS feels this deeply because satellite clocks live higher in the field. General relativity makes them gain about 45 microseconds each day. Special relativity makes them lose about 7 microseconds from speed. The net is 38 microseconds per day, unless corrected carefully. Engineers preload offsets and model Earth's multipole gravity in software. Without those steps, your map pins would slide kilometers each day. Example in real terms: timing errors of nanoseconds mean meter-level misses. Aviation, finance, and phones quietly lean on this relativistic bookkeeping. Bottom line, bending is what rulers and clocks collectively report everywhere. Deep underground, a gamma ray climbs a vertical shaft toward daylight. Static curvature can shift energy, even when nothing visibly changes. You care because redshift and time dilation work in steady fields. Geometry stays fixed, yet light loses energy while climbing upward. Frequencies drop because lower clocks tick slower than higher clocks nearby. That difference exists without sources moving or fields waving in time. The Pound-Rybka experiment measured a tiny shift using iron gamma rays. The fractional change was about 2.5 times 10 to the minus 15. Later, optical clocks placed just 33 centimeters apart disagreed measurably. Their fractional offset was near 4 times 10 to the minus 17. Those numbers match predictions using Earth's surface potential difference precisely. Another test bounced signals past the sun, seeing Shapiro delay in microseconds. Nothing pulsed at the source, yet the travel time still stretched. Astronomers and metrologists now track these shifts to calibrate instruments. Even elevator rides change tick rates, although by absurdly tiny amounts. One sentence recap: steady curvature leaves fingerprints in quiet laboratory arrangements. A quiet grid bends near a mass and light arcs obediently. That was the whole trick from the start, not motion. If the picture clicked, you now see gravity as geometry. It is a shape that guides paths even when sources pause. We watch stars deflect light, clocks drift, and triangles misbehave slightly. All of it unfolds while the wider scene can look still. Recap in one breath: change the metric and paths change themselves. Every test we cited agrees, from eclipses to GPS corrections. You can keep building intuition by picturing the stage, not forces. When the stage curves, straight lines curve and nothing must shove. I would love to keep exploring these strange but clean ideas. Want more clear explainers on space, time, and hidden structure? Tap subscribe if this helped and share it with a friend. Before you go, replay the opening claim and notice the calm logic. Space bends, so paths bend, no moving parts needed.